for a 2D body? 3, right? And what are they? Some of the forces in the x, some of the forces in the y, some of the moments in the z. Okay. 3D, how many equations do I have? 6. Some of the force equations, right? X, y, and z. And the sum of the moments equations, x, y, and z. Okay. So now, when we start entering friction, what changes? What do we now have? We have another equation. And what's that equation? The frictional force is equal to mu times z. So if we're talking about a two-dimensional problem, how many equations do we have now? We have 4. Some of the forces in the x equals 0, some of the forces in the y equals 0, some of the moments about the z equals 0, and then our frictional equation. So in the past, for 2D problems, we could solve for at most how many unknowns for a 2D problem? 3 unknowns. We could only solve for 3 unknowns because we only had 3 equations. But now that we've introduced the friction equation, how many unknowns can we have? 4 for a 2D body. Okay? And a 3D body, in statics we typically we're not doing 3D problems in friction, but if we did, let's think, how many equations would we now have? The potential. Okay, well we have, in the x direction, we have a force equation, a moment equation, and a friction equation. And in the y, we potentially could have a force equation, a moment equation, and a friction equation. And then in the z, yeah, we have 9. Okay? But it depends on which way movement is going. When can we apply that frictional equation, F is equal to mu n? When?
When it's either kinetic or
When it's kinetic or static, but since we're just dealing with statics right now, when can we apply that static friction equation? When there's impending motion, when it's about to move. If it's not moving, you can't use the friction equation. And we proved that in that second problem we did, where we had a block on a block. Do you remember? We could not use the friction equation. So how many of you have looked at friction? I mean, you just handed in the frame homework, so probably not too many people, or 4 or 5 people. It's really good to look at the topic. If we're continuing friction, it's always good to spend at least 15 minutes looking at the friction stuff that we did, right? So you prepped for today. So in the 2-block problem, we couldn't apply the friction equation because we didn't know if those blocks were moving relative to each other. And we proved from the math that they weren't, right? Because the friction equation didn't work. Okay, so go back and look at that problem again. We're going to do 2 more problems. When we deal with friction, we're dealing with sliding problems, right? Which is translational motion, right? But I could also what? Tip, right? I could have rotational motion. So if there's enough friction and there's a lot of weight up here, I might actually tip rather than slide. So far we've done 2 sliding problems. We did the 1 block on the inclined plane. We did 2 blocks on top of each other on a horizontal plane. Now we're going to look at 2 more problems where we're going to look at rotation. Okay? So let's look at the first one. And everybody should have a copy. It's up here. You ready?
Yes.
Ready?
Yes.
Okay, problem 1. 250-pound cylinder shown in the figure is in equilibrium on the inclined surface. Determine the weight W and the minimum coefficient of friction between the inclined surface and the cylinder. So, first thing, given the weight. So, but you don't want to use the variable W because they already have a W there. So you want to say like, how about WC? The weight of the cylinder is 250 pounds. Okay, and nothing else. Find, what do we have to find? W and U. So let's make our table. Force, moment, magnitude, direction, and Clara, let's start with you. So So what forces are present here?
WC.
WC, okay.
W.
Do we know the magnitude?
Oh, WC, yes.
Direction,
Yes.
okay. What's the next one?
We got the other W.
Okay, do we know the magnitude?
No.
No, direction,
Yes.
right. What else?
We have normal.
A normal. And since this is scrap, I'm gonna just, write on this thing. Where's our normal? It's going up this way, right?
Yes.
And since you love these angles, I'm gonna
Oh,
ask you to
God, I know.
find out where the 30 is.
Or the 30-degree angle.
Goes between the normal and,
The upper right part of the surface, or that?
it's either horizontal or vertical line. So it's either between this and the X or this and the Y.
X.
Try again.
Why?
Why? Because look,
Really?
the inclined surface and the horizontal surface is 30 degrees,
Yes.
right? This here is 30 degrees, which means since this is perpendicular to this guy, I need a line that's perpendicular to this, so it's gotta be here.
Okay.
Two things perpendicular, two things same angle.
Okay, just opposite perpendiculars.
Right. So the normal, we don't know, and the direction we know.
We have mu.
Okay, and mu isn't a force or a moment, right? So it's what? We're really looking at the
F.
frictional force.
And,
Do we know the magnitude?
no.
No. Do we know the direction?
Yes.
Yes. And which way do you think this thing is gonna move?
Down.
Down, so the frictional force goes?
Opposite.
Right, up. So Javen, so far, how many unknowns do we have looking at this table?
3.
3, but we have to remember that they also gave us a mu that we have to find. Right? So how many unknowns do we have total? Javen?
Well, I'd still say 3 because you find F through, find U through F and N.
Right, but that's
I-
when we start putting in equations, right? Right now, W is unknown, N is unknown, the frictional force is unknown, and mu is unknown.
But mu's in your F there, so why would you include that on your table?
But we need that equation, right? So what you're doing is saying, oh, mu F, the frictional force is equal to mu N, so
Sorry,
you're
yes,
using
sir.
that equation to find out the relationship between those two. So in the past, we always said how many unknowns we had, right? And then we figured out what equations. Well, you already know that one of the equations you're gonna use is the force, the friction force equation. But you also know, what other equations are you gonna use, Jabin?
Some of the moments in the
Some of the moments about Z,
Z and some of the moments are forces in X and Y.
force in the X and Y, and then the friction equation. So we're gonna use all 4 equations because we do have a sum total of 4 unknowns.
So why do we not put mu in the table?
Well, we don't really have a column for it.
So it's
It's
just
not a
gonna be floating
force, it's
unknown?
not a moment, I mean, I don't know, oh, you wanna put it here? No, mu is a coefficient, it's not a force, a force is a push or a pull. It's a wear surface, it's a characteristic of a surface.
How many unknowns would you say are there then?
There's 4. So there are 1, 2, 3 unknowns, plus we have this guy, so we have 4 unknowns. So we need 4 equations, and how many bodies do we need? 1 body. Rachel?
I'm confused about the question. Like, what is the weight? The weight W, isn't that given to us?
There are 2 W's.
I don't understand what the 2 W's
Okay.
difference is.
So here there's a W of a block, right? So there's a suspended weight that's trying to keep this guy, the cylinder, from sliding down. But there's also the weight of the cylinder.
Right.
The cylinder has weight,
Oh, the weight.
and then the weight of that little block is trying
thinking
to.
that was a pulley or something.
Say it again?
I was thinking that was a pulley.
You could view it as a pulley, certainly.
I didn't know, but I just got confused about like what weight you're finding.
Okay, so there are 2 different W's. They're telling us that the cylinder, in the drawing, they have a W ready, right? So I didn't want to use the same variable,
Yeah, that just looked like a cylinder to me.
right? But doesn't it have a W on it?
Yeah. I
Right.
just got confused.
Okay, so they're asking us, they're telling us that the cylinder is a weight of 250, so that's why I called it WC, the weight of the cylinder. And then it, as you go on, it says determine the weight W. I think I'm just reading it too fast. Since I already know the problem, I'm probably not giving you enough time to read it. So let me give you more time to read the problem, okay? So there are two weights. There's the weight of the thing that's suspended, that's trying to hold it up, and then there's the actual weight of the cylinder. Good?
When you do WC and WB, just with a block.
You can make it a WB for block, but they're already calling it W, so why change it? Because if you introduce another variable, for me, that's when I would get confused. Because now I just called something WC, I just called something WB, and the problem is calling it W. So I would probably continue to use the variable that they have. Okay, so what body do we want to analyze then, Aaron?
I would say the cylinder.
The cylinder. So let's draw the guy. This is 8, this is 12. I have my WC, I have my normal, I have my 30 degrees. I have my friction force. And then I have this W coming down. I didn't draw the axes yet because we have to decide on it. And I have to show those two circles inside because the frictional force is on the outside of the circle, but the W is on the inside of the circle. So Aaron, since you were picking the free body diagram, which way do you want to orient the axes? Which is the one we know?
I want to put the X.
Hang on a second, we know WC, right? So I'm gonna put 250 pounds on here. And these are the guys that are the unknowns. Okay, so what do you wanna do?
I would put the X in the frictional force and the Y in the normal.
Okay, the X and the what? The
Frictional force.
friction. So going over to the side, does that sound good to everybody?
So frictional.
Okay, so the option is either to put your X and Y axis like this, and then these two guys lie in that axis, and we're gonna have to find components of these. Otherwise, we put our axis like this, and now we have to find components of these two. The fact that this value, this number, this force has a value, that's gonna be easier to find components of. So I would agree with Aaron, but it doesn't matter. You can do it, you can do it like this, you can do it like this. Okay? You're trying to orient your axis in a direction that'll decrease the amount of work you have. So let's do that. Let's say that this is my Y, and this is my X.
I think your angle is wrong, or you're not matching up from the original and the second.
This is 30 degrees, right?
But you have from the weight of the block to the normal, and now you have the weight of the.
It doesn't matter because that's all I need to know is that this and this are the, I see what you're saying, Chris, but this of 30 is the same as this of 30.
Okay.
Because the idea is that the normal is 30 degrees from the y-axis, and both these forces are in the y.
Cool.
Okay? So if we go back to you guys are experts on doing statics problems, given, find, table, unknowns, figure out how many free body diagrams, draw the free body diagram, what's the next step? Find the components, right? And then we can do our checks. So which forces do we have to find the components of? W, C, and W, right? Okay, so WC is equal to 250 times the cosine of, okay, let's see, if I do X, it would either be the sine of 60, or I could say the negative cosine of 60. No, I could say the sine of 30. Can we write all these? Because it's nice for you to be comfortable with all these. So WCX component is either equal to 250 times, what we've always done is we've used the direction angle. So the direction angle to the positive x-axis would be 90 plus 30, which is 120. Is everybody also equal to, that it's double, times the cosine of 60, but it has to be a negative. Or I could say WCX is equal to 250 times the sine of 30 negative. What I want you to do is write these three down, and we're not going to think about it now because this is trig, and you know this, you just need to refresh your memory on it. But write these three things down, and then look at them later. So WC is equal to 250 times the cosine, let's do it of the direction angle, which is what we used to do in the past. And then it's 180 minus 30, which would be 150. Cosine of 150, J, and it's in pounds. Comes out to be 250 times, what is this? 0, is it 866 or a half? Calculators, where are the calculators?
Negative half. Negative 0.
How do you guys remember? I don't remember. Minus 0.8660 pounds.
Y 216.5.
So it comes out to be what? 125I negative minus 216.5J pounds. So which check do you want to do?
Unit vector.
Or what are the two possibles you could do?
Unit vector.
The magnitude check, the magnitude vector, square this under the radical should equal 250, or
Unit vector.
do the unit vector check. So do one of them. Either do the unit vector check or the magnitude check, so that you know, yeah, that's great, I'm fine. Feel a sense of accomplishment partway through the problem. And then what's the other one we have to do? W, right? So W is equal to W times, isn't it the same? We're looking at the same angle, so it's negative 0.5I minus 0.866 J, and we know we're working with pounds. So it's negative 0.5 W I minus 0.866 W J, and we're dealing with pounds. So this is W, and this is WC. And you could do a check here as well. But here, what check can we do here? Only the unit vector check, because we don't have the magnitudes. So Maria, we talked about having, there are 4 unknowns here, the 3 forces and the coefficient. So we need 4 equations. So which equation, if we do sum of the forces in the x, how many unknowns are we gonna have in it? Two, which ones?
The
Frictional force and
The W.
W. If we do sum of the forces in the y, how many unknowns do we have? Keep going, Maria. Two, which are
A normal.
the normal and the W. If we do sum of the moments, where would you like to do sum of the moments about?
The y-axis.
How about the origin, the center? If we do sum of the moments about the origin, how many unknowns do we have? Two again, which ones? The frictional force and W.
You can do it at
So we're not really,
you can do it at the point where they intersect and then have the friction.
okay, so like right here?
Yeah. And then you only have one. So in the moments at that point, then you only have W.
WC.
Well, W unknown.
But how do you know they all converge? You have to do the geometry. I have to draw everything to scale to find out if it really does converge. So certainly if I do it at this point, normal and frictional force intersect at that point. So I would have WC and W, but I don't know what that distance is going to be. You have to really draw it to scale and see what the distance
The
is.
force in the X times its perpendicular in the Y and then the force in the Y. The component of that.
Yeah, but you don't know what the perpendicular distance is. What is the perpendicular distance between where these guys cross and where this crosses that point? So we're gonna have to do it about the center. And then what about the frictional equation? Back to Maria, how many unknowns do we have in the frictional equation? Two, because we have a frictional force and we have mu. And we have n. So there's no great equation to do, so let's just do them all. Let's see how fast you can do all four equations. You ready? Okay, go.
So if you were to do at this point,
But this doesn't cross. Okay, 20 seconds went by. Well, let's see how fast you can get all four equations. Okay, 1 minute went by. Tell me when you get W. Right, so in,
I'm using the equation to
okay, so,
this is a new thing that
where there's, yeah, right, where you might have 10 unknowns. So in the framing problems, we found that there might have been 10 unknowns, right? But we only needed to find one of them, so we did the table, we saw, oh, 10 unknowns, oh my God, I'm gonna need to have so many three-body diagrams. But then once you look at the three-body diagrams, you would say, okay, well, which would be the most efficient way to solve it, and maybe you don't even go kind of build it, solve it.
Cause then, I mean, it seems like that's what you do is like just constant now. How you use it as a tool, like, okay, well, that's something that's.
Well, the idea of the table, the main purpose of the table is for you to identify all the forms of